For most of the world, Greenland is a frozen, distant landscape, silent, white, untouched. A vast expanse of ice stretching over 800,000 square miles, holding within it the second largest ice sheet on Earth. It's a place people often associate with stillness, with frigid winds and ancient glaciers slowly grinding their way toward the sea. But beneath that silence, beneath the miles of solid ice and permafrost, something unexpected has begun to stir. It began with a series of heat anomalies, unusual thermal signatures that seemed to rise from deep beneath the frozen crust. At first, they were dismissed as noise, or calibration errors, or perhaps even glitches in the satellite imaging data. After all, what kind of heat could possibly be emerging from under a slab of ice nearly 2 miles thick? But the readings persisted. They came from multiple instruments, confirmed by multiple sources, and began appearing with a consistency that was impossible to ignore. These weren't surface-level temperature fluctuations caused by the sun or shifting air currents. These were signals radiating upward from within the Earth itself, unexpected, uneven, and intensifying. Greenland is no stranger to geological activity. It rests on a relatively stable part of the Earth's crust, with no major fault lines or active volcanoes in recent memory. But that's what makes these findings so unusual. Because buried beneath a land covered in ice, where very little is supposed to be happening at all, researchers are now detecting pockets of elevated heat, zones where the underground temperature appears to be rising, slowly but noticeably. This isn't the kind of heat you would feel if you were walking above it, not yet at least. But in the world of geophysics, even small changes matter. A 1-degree rise underground, in the right place, can alter the pressure of subsurface fluids, destabilize frozen sediment layers, and set off chains of events that ripple outward through the environment. Especially in a place like Greenland, where the balance between ice and water is already razor thin. The scientific community has taken notice. Research teams from multiple institutions have begun to pore over satellite thermal imagery, cross-reference ground-penetrating radar scans, and review historical data logs to understand what, exactly, is happening. The presence of geothermal heat beneath Greenland isn't new in theory. What's new is the behavior. The pattern. The change. Some of the detected anomalies are situated near known subglacial lakes, bodies of liquid water trapped beneath the ice, kept from freezing solid by warmth from the Earth's core. But other hotspots are appearing in unexpected locations, in areas where there should be no significant thermal activity at all. And that's where the real questions begin. What is generating this heat? Why is it showing up now? Is it a natural fluctuation in geothermal energy, or the early sign of a deeper shift in the Earth's crust? Could it be linked to broader tectonic processes, ones that we've previously overlooked, or perhaps never even imagined? None of these questions have definitive answers yet. But what's clear is that something unusual is unfolding beneath Greenland's icy surface. A silent process, hidden from view, quietly rewriting what we thought we knew about one of the most remote and stable regions on Earth. What we're seeing may be the first tremors of a deeper mystery, a hidden pulse rising from within the planet, shaking loose secrets buried beneath millennia of ice. And while it's still too early to draw conclusions, the data is speaking. Now, it's up to us to listen. Because when the ground beneath a place like Greenland begins to warm, the world should pay attention. Now, before we continue, I would like to remind you to consider subscribing and liking the video in order to support us. Back to the video. Among the many theories being examined by scientists and geophysicists, one of the most compelling, and perhaps most grounded in geological precedent, is the idea that the anomalous heat signals might be caused by a resurgence of geothermal energy from an ancient mantle plume. This is not just any minor blip in Earth's internal thermostat. We're talking about a colossal, slow-moving column of hot rock rising from deep within the Earth's mantle, potentially having simmered for millions of years beneath the surface, now quietly releasing heat under the Greenland ice sheet. To understand why this is such a plausible and intriguing explanation, we first need to look at what a mantle plume actually is. These are not surface-level features like volcanoes or earthquakes. Instead, mantle plumes are thought to originate from near the boundary of Earth's core and mantle, roughly 1,800 miles beneath our feet. Over vast spans of geological time, these plumes carry heat upward through the mantle, eventually causing regions of the Earth's lithosphere to bulge, weaken, or even melt in localized spots. The most famous example of a mantle plume is the one that created the Hawaiian Islands. Another gave rise to Iceland's volcanic terrain. These are surface expressions of what can happen when a plume makes contact with the crust and breaches the Earth's exterior. But what makes the Greenland case so curious is that if a mantle plume is involved, it hasn't yet reached the surface. Or perhaps it never will. Instead, it may simply be lingering beneath the crust, slowly releasing enough thermal energy to disturb the frozen equilibrium of the island's subsurface environment. This hypothesis isn't purely speculative. In fact, there's already evidence suggesting a plume-like anomaly beneath central Greenland. A 2016 study led by scientists at NASA's Jet Propulsion Laboratory used radar and gravity data to model the conditions beneath the ice. What they found was a region exhibiting unusual geothermal flux, a fancy way of saying, there's a lot more heat here than we expected. And that heat isn't just an academic detail. It has very real effects. In regions where the ice sits directly above these thermal pockets, the base of the ice sheet may begin to melt from below, creating what are called subglacial lakes or slippery zones, areas where the ice can begin to move faster, destabilize, or even collapse. But what's especially telling is that these regions also seem to align with where the new thermal anomalies are being detected. The suggestion? That the heat may not be randomly distributed at all. It may be part of a deeper, focused upwelling of geothermal energy. Here's where things start to get really interesting. Mantle plumes aren't sudden events. They don't just flare up overnight. Their movement and thermal release occur over millions of years. But sometimes, their effects can become more noticeable when conditions above them shift, say, due to ice loss, crustal thinning, or tectonic adjustments. And Greenland, in its own quiet way, has been undergoing precisely these kinds of changes. Over the last several decades, satellite data has confirmed a steady loss of ice mass from Greenland's surface. As the weight of that ice decreases, the land beneath it slowly begins to rebound, a process called isostatic adjustment. Think of it like removing a bowling ball from a trampoline. The surface slowly rises after the weight is taken away. But in doing so, that shifting pressure can influence the deeper layers of the Earth, potentially allowing long-contained geothermal heat to rise more freely toward the surface. So we have a convergence of factors, a subsurface heat source that may have been present for millions of years. A shifting crust, lightened by melting ice, creating new paths for that heat to travel. And newly detected anomalies appearing in precisely the areas where we would expect such a thermal release. But why now? One theory is that this is all part of a delayed feedback loop. The mantle plume beneath Greenland, if it truly exists, may have always been there, but only now, in the context of modern climate shifts and glacial retreat, is its influence becoming visible. That is to say, the Earth is responding to changes on its surface, and in turn, those changes are triggering responses from within the Earth itself. Another possibility is that the plume's thermal intensity has subtly increased over time. This wouldn't necessarily mean a dramatic spike in heat, but even a minor uptick could be enough to disrupt the delicate balance beneath Greenland's ice. After all, we're not talking about a tropical island or a volcanic arc here. We're talking about a place where everything depends on the cold staying constant. A few degrees can be the difference between stable permafrost and cascading ice melt. The implications of a mantle plume beneath Greenland are wide-reaching. For one, it would fundamentally reshape how we understand the geology of the region. Greenland has long been considered relatively inactive in terms of tectonics and volcanism. If we now suspect there is a long-term heat source beneath it, one capable of driving changes in the ice sheet above, it would mean revising our maps of geothermal activity, and perhaps even rethinking the future behavior of the ice itself. Moreover, if the plume is growing in intensity or mobility, we might begin to see secondary effects. This could include the formation of new subglacial lakes, increased glacial flow rates, or even changes in seismic activity, not due to tectonic fault lines, but as a response to shifting heat and pressure beneath the surface. Of course, all of this still exists in a realm of scientific investigation. No one has drilled deep enough into the Greenland crust to directly sample mantle rock. The evidence we have is indirect, based on thermal readings, gravity anomalies, and models of crustal behavior. But the pieces are beginning to line up in ways that are difficult to ignore. If this plume exists, and if it is the true source of the heat anomalies, then we are witnessing a slow, silent geological process beginning to leave its fingerprint on the surface. The ice above is responding, the ground beneath is warming, and deep within the earth, an ancient engine may be turning once again. This isn't a volcanic eruption. It's not a fault line fracture. It's something deeper, older, more methodical. And the question now is, what happens next? As scientists delve further into the mantle plume theory, one question becomes increasingly critical. If a plume is indeed the root of this subterranean heat, how exactly is that heat interacting with the structure and composition of Greenland's crust? Beneath the icy veneer, Greenland's crust is far from uniform. It's a patchwork of ancient continental fragments, sutured together over geological eons, many of them dating back over 3 billion years. These are not soft, recently formed rocks, but ancient, stable cratons, sections of the Earth's crust that have remained largely undisturbed for immense periods of time. But even ancient formations aren't impervious. A mantle plume doesn't need to blast through rock in a volcanic display to cause change. It can instead seep, distort, and warp the land above over time, exploiting microscopic fractures and pre-existing weaknesses in the crust. In Greenland's case, this means that areas where the crust is thinner, fractured, or compositionally distinct could serve as preferential pathways for this rising heat. And here's the critical part. These pathways might be almost invisible from the surface, hidden under kilometers of ice and unreachable by conventional seismic observation. Yet indirect signatures begin to emerge. For instance, variations in crustal conductivity, a measure of how easily heat and electricity pass through rock, have been mapped across Greenland using magnetotelluric surveys. In some of these areas, conductivity anomalies coincide with the same regions where heat is now being detected. That raises a fascinating question. Is the crust itself acting like a conduit, enabling deeper thermal energy to migrate upward more easily than we once thought? Adding to the complexity is the behavior of the lithosphere, the rigid outer shell of Earth that includes the crust and upper mantle. Underneath Greenland, the lithosphere may not be uniformly thick. Some models suggest that portions of it have undergone intracontinental stretching in ancient times, possibly during the opening of the North Atlantic millions of years ago. If these stretched regions remain today as thinner lithospheric pockets, they could be acting like geothermal windows, allowing heat from the deeper mantle to influence the base of the ice sheet more directly. And while a mantle plume is typically portrayed as a singular column of rising rock, the reality may be far more fragmented. What if, instead of one central plume, we're dealing with multiple diffuse upwellings, smaller branches of thermal energy radiating outward from a broad, partially molten zone beneath Greenland's crust? In that case, the anomaly detected today might not be a standalone heat source. It could be just one tendril of a much larger, more complex mantle system slowly awakening from dormancy. This opens up another avenue of investigation, the role of ancient magmatic provinces. Deep within Greenland's crust lie the ghost signatures of massive volcanic events from the planet's distant past. While long since dormant, the residues of these events, known as plume heads or lithospheric scars, can still affect how heat flows today. If a modern plume were to rise beneath such a feature, it might find its ascent influenced by the thermal and chemical heterogeneity left behind. In short, the plume's heat might not be behaving like a simple vertical elevator. It could be bending, diffusing, and warping through a maze of pre-existing subterranean architecture. Some researchers are also examining how the chemical composition of the mantle beneath Greenland could affect the behavior of any potential plume. Certain types of mantle rock, especially those rich in radioactive isotopes like uranium, thorium, and potassium, naturally generate heat over time through radioactive decay. If a plume is interacting with such enriched material, it could amplify its thermal signature, essentially becoming hotter than an equivalent plume elsewhere. This could help explain why the detected geothermal fluxes seem unusually strong for a region not known for recent volcanic activity. Moreover, the movement of heat itself within the Earth isn't as straightforward as one might assume. While we tend to imagine it traveling in a direct upward path, mantle dynamics are influenced by complex convection patterns, pressure gradients, and mineral phase changes. In this case, the heat beneath Greenland could be deflecting laterally, trapped between layers of differing density or composition, then redirected upward only when it encounters a structurally weak zone. This could result in patchy, uneven warming at the ice sheet space, just as we are currently observing. All of this paints a picture not of a singular dramatic event, but of a slow-burn geological process playing out beneath our feet. A gradual unzipping of thermal boundaries. A whisper of deep earth processes usually hidden from human awareness. And then there is the silence. Unlike volcanoes or earthquakes that announce their presence with violence and disruption, a rising mantle plume beneath Greenland would do none of that. Its signal would be muted, diffuse, almost invisible, detectable only through sensitive instruments measuring gravitational anomalies, electromagnetic fluctuations, or the subtle ways in which ice above it begins to behave differently. That's what makes this theory so hauntingly compelling. It's the quiet that speaks volumes. A plume doesn't need to roar to reshape a continent. It can whisper. It can wait. And in the cold isolation beneath Greenland, it may be doing exactly that, an ancient heat slowly pressing upward, not to erupt, but to influence. To thaw. To move. At the intersection of geological memory and modern observation, scientists now find themselves faced with the task of deciphering a riddle written in the language of heat, pressure, and stone. It's a language spoken not in years or even centuries, but across the vast, yawning epochs of Earth's deep time. And if the plume is indeed the voice behind that riddle, then the answers, though slow in coming, may one day rewrite our understanding of Greenland's place not just in the cryosphere, but in the Earth's deep, churning interior. While the mantle plume hypothesis provides a tantalizing explanation for the mysterious underground heat signals detected beneath Greenland, it's far from the only contender. As researchers peel back the geological layers in search of answers, another compelling possibility has emerged: deep crustal fault activity. At first glance, Greenland may seem like an unlikely candidate for fault-driven geothermal activity. After all, it isn't located along the edge of a tectonic plate, where most of the planet's seismic and volcanic activity takes place. The island sits squarely atop the North American plate, far removed from the grinding plate boundaries that dominate the Pacific Ring of Fire or the volcanic belts of the Mediterranean. But appearances can be deceiving. In recent decades, scientists have discovered that even areas far from active plate boundaries can harbor ancient, reactivated fault zones, zones that, under the right conditions, can channel heat upward from deep within the Earth. These faults are not young, dramatic fractures tearing through the Earth's crust with cataclysmic force. Instead, they are stealthy relics of a violent past, geological scars left behind by long-extinct tectonic episodes. Some date back hundreds of millions of years, to when the supercontinents of Rodinia and Pangaea were assembling and breaking apart. During those ancient times, Greenland was anything but quiet. It was caught in the tectonic crossfire, squeezed, stretched, and shattered by colliding land masses and shifting lithospheric plates. Though the violence has long since ceased, the structural imprints remain etched into the crust like the weathered bones of an ancient beast. Now, scientists are beginning to wonder, could these ancient faults have quietly come back to life? Even a slight reactivation of a deep fault line can have profound consequences, not by shaking the ground, but by creating vertical pathways through which heat from the mantle and lower crust can migrate upward. In regions where faults cut deep into the Earth, they act like thermal expressways, bypassing the insulating upper crust that would normally trap heat below. In Greenland, where vast ice sheets press down with unimaginable force, the pressure may actually help to compress and warm faulted zones, subtly changing their permeability and encouraging upward thermal flow. One fault system in particular has drawn the attention of researchers: a buried shear zone stretching across a portion of southern and central Greenland. While not well understood, due to the sheer depth and the logistical difficulty of direct study, this structure appears to correlate with areas of anomalous basal ice melt and subglacial lake formation. The heat signature doesn't lie. Where this ancient fault dips toward the mantle, strange thermal anomalies begin to bloom, surfacing not as earthquakes or eruptions, but as persistent warmth beneath thick, unmoving ice. Unlike a mantle plume, which might produce a focused dome of heat, fault-related thermal upwelling can be more diffuse and fragmented, creating patchy zones of geothermal flux. This could explain why the heat signals beneath Greenland appear inconsistent, hot in some areas, but not in others. These inconsistencies may mirror the hidden geometry of the fault itself: bends, splays, intersections, and fractures deep beneath the crust, each one a potential leak point for Earth's hidden warmth. Complicating matters further is the presence of fluid migration within the fault zones. In many active fault systems across the globe, superheated fluids, rich in minerals and gases, travel along fractures, transferring heat more efficiently than dry rock alone ever could. If similar fluids are present beneath Greenland, they might be responsible for amplifying the warming effect, even if the fault itself isn't currently slipping or producing measurable seismic activity. The fluids would act like invisible currents, carrying heat from depth and distributing it along unpredictable pathways. What's particularly intriguing is how this theory aligns with certain seismic low-velocity zones detected in Greenland's subsurface. These zones, regions where seismic waves travel unusually slowly, are often associated with high temperatures, partial melts, or elevated fluid content. In other words, they are the footprints of heat in hiding. Several of these anomalies are located suspiciously close to the suspected fault structures, hinting at a deep interplay between old tectonics and modern thermal dynamics. In this context, Greenland becomes a geological paradox, a region thought to be tectonically inert, now showing signs of quiet subsurface activity. It's not the kind that makes headlines. There are no tremors felt in nearby towns, no smoke rising from icy valleys. But beneath the surface, the Earth might be shifting in subtle, silent ways, and the heat is the only clue we have. Of course, detecting and confirming the existence of fault-driven heat flow is a monumental challenge. Unlike open faults visible at the surface, Greenland's deep crustal fractures are completely hidden beneath thick layers of bedrock and ice. Scientists rely on indirect methods: gravity mapping, seismic tomography, magnetotellurics, and deep ice core temperature profiling. Each dataset offers a fragment of the larger picture, a blurry window into a hidden engine far beneath the surface. Even the behavior of the ice sheet itself may be whispering clues. In some regions, scientists have noted unusual patterns of basal lubrication, where the underside of the glacier appears to be melting more quickly than surrounding areas. These melt zones correspond suspiciously with thermal anomalies and fault-aligned structures, offering potential evidence that deep crustal heat is influencing glacial dynamics, perhaps more than we ever anticipated. What makes this theory especially captivating is its dual nature, both ancient and ongoing. The faults in question were forged in the heat of prehistoric collisions, but today, they may be acting as living systems, quietly shaping the thermal evolution of Greenland from below. In a sense, they are ghosts of geological trauma, continuing to affect the landscape long after the wounds were supposedly healed. And while this cause may lack the dramatic flair of a mantle plume, its implications are no less profound. If ancient faults are still acting as thermal conduits beneath Greenland, it could mean that the island's thermal landscape is not static, it's dynamic, evolving, and far more active than once believed. Such a realization would force scientists to reevaluate not just Greenland's geology, but the thermal histories of other so-called stable regions around the world. As we continue to probe the icy depths with increasingly sophisticated tools, we may find that the secrets of the past, buried deep in rock and time, are still very much alive beneath our feet. Faults that once tore continents apart may now be feeding silent rivers of heat into the base of the Greenland ice sheet, reshaping it one hidden degree at a time. building upon the foundation of ancient fault systems as a plausible source of Greenland's subterranean heat. Scientists are beginning to unravel even more intriguing complexities buried within this quiet theory. These aren't just leftover fractures. They're part of a deeper network of geological structures that may stretch farther and function more dynamically than once assumed. As research advances, the narrative around these faults has begun to shift, not from isolated relics, but as part of a vast, interconnected system of hidden geothermal veins still subtly shaping the landscape from below. A crucial aspect that's gained renewed attention is the interplay between lithospheric thinning and localized extension, geodynamic processes that, while typically associated with active rifting environments, might also have left a lasting fingerprint beneath Greenland. In certain regions, especially those affected by historical tectonic stretching, the crust can become unnaturally thin and riddled with zones of weakness. Over geological timescales, these weakened areas don't just vanish. Instead, they can linger like underground fault corridors, susceptible to reactivation under the right pressure-temperature conditions. This raises a captivating possibility that some of the faults beneath Greenland may not be operating alone, but instead forming part of larger, nested fault complexes, quietly channeling heat upward through intricate, crisscrossing pathways. These interlinked zones could act like a slow-breathing thermal circulatory system, pulsing geothermal energy toward the surface in an irregular but persistent manner. Unlike volcanic activity, which erupts suddenly and violently, this kind of geothermal expression is far more subtle, diffuse, episodic, and extraordinarily difficult to detect without sustained, high-resolution observation. Adding to this quiet complexity is the potential role of metamorphic core complexes, deep crustal formations that can form when ancient fault zones expose high-temperature rocks nearer the surface through slow uplift. These complexes often act as conduits for residual heat long after their tectonic origins have faded from memory. Beneath Greenland, it's possible that remnants of such complexes exist far below the ice, buried beneath kilometers of sediment and crystalline bedrock. If even partially intact, they could serve as thermal anchors, holding on to heat over millions of years and gradually releasing it through structural weak points. Some geologists have theorized that during the last major glacial retreat, the sudden unloading of ice mass may have caused post-glacial rebound, a slow upward motion of the crust as it adjusts to the absence of weight. This seemingly minor adjustment might have been enough to reawaken dormant faults, shifting rock boundaries just enough to re-establish permeability and allow heat to begin trickling upward once again. It's a reminder that Greenland's geological story isn't just about ancient processes. It's also about recent changes, and how the Earth's crust continues to react to both past and present forces. In fact, even microscale faulting, subtle, hairline fractures running across the base of the crust, could play a role. These aren't major fault lines that tear continents apart, but they can still create localized zones of elevated temperature by offering channels for fluid convection. When water or brine-rich fluids are present, even at modest depths, they can transfer geothermal energy with remarkable efficiency. A slight shift in pressure, a minor increase in fluid content, and suddenly these microfaults become miniature radiators, warming the bedrock and the base of the ice above them with quiet persistence. Interestingly, the temperature data collected from various ice cores across Greenland reveals anomalous basal temperatures that don't neatly correspond to surface conditions or known geothermal gradients. In several sites, the ice sheet appears to be melting from below, but not due to atmospheric warming or solar input. Instead, the heat seems to rise from the crust itself, concentrated in unexpected pockets and bands, some of which suspiciously align with the projected locations of buried fault systems. These thermal fingerprints offer a faint but provocative clue that fault-related geothermal activity may be far more widespread than current models predict. One of the most confounding aspects of this phenomenon is how inaccessible and indirect the evidence truly is. Scientists cannot directly peer into the depths of these ancient faults. Instead, they rely on inference from seismic wave behavior, gravity anomalies, magnetic field variations, and thermal flux patterns, each of which paints an incomplete picture. Yet, as more data is gathered and layered together, a larger pattern begins to take shape, a pattern that speaks not of random anomalies, but of a hidden heat delivery system embedded deep within Greenland's crustal architecture. This is where high-resolution geophysical modeling becomes indispensable. By creating advanced simulations of Greenland's subsurface, researchers can begin to test how different fault orientations, depths, and fluid contents could influence thermal flow. Some of these models suggest that even minor fault reactivation, when aligned just right with natural heat gradients, could create temperature anomalies consistent with those being observed today. In other words, the data fits, and that's no small thing when dealing with geologic structures buried beneath kilometers of ice and stone. Complicating matters further is the possibility that tectonic reactivation may still be ongoing, albeit at an extremely slow pace. Even minuscule movements, measured in millimeters per year, could be enough to fracture crustal rock and enable deeper thermal reservoirs to leak upward over time. Greenland's subsurface is not static. It's a landscape of creeping shifts and gradual realignments, occurring on timescales far beyond human perception. And within those shifts, the hidden heartbeat of geothermal exchange may be pulsing quietly onward. In the absence of volcanic activity or dramatic tectonic plate boundaries, Greenland's deep faults are a reminder that not all geological activity is loud. Sometimes the most profound changes are the ones that unfold silently, buried beneath layers of time and ice, detectable only by the heat they leave behind. These ancient fault systems, once dismissed as inactive scars of a distant era, are now being re-examined through a new lens, not as dead zones, but as subsurface lifelines, quietly shaping the dynamics of one of Earth's most enigmatic regions. While the theory of fault-driven geothermal activity provides a compelling and scientifically grounded explanation for the heat anomalies detected beneath Greenland, not all researchers are content to stop at what we already know. Beneath the layers of empirical observation and geological modeling lies a growing fascination with the unknown, the liminal space where established science blurs into frontier speculation. In this space, a second potential cause for the anomalous heat signals begins to take form, not born from tectonic strain or crustal weakening, but from something altogether more enigmatic, more veiled in complexity. Some scientists, albeit cautiously, have proposed that unusual electromagnetic fluctuations detected in conjunction with the heat signals may hint at a different kind of subterranean activity. Unlike the steady and expected outputs of geothermal systems, these fluctuations appear irregular and erratic, pulsing in patterns that defy conventional explanation. More intriguingly, their origin seems difficult to pinpoint, not diffused over wide areas like typical crustal heat, but instead localized, almost as if radiating from a very specific source buried deep beneath the surface. This has led to a fringe but tantalizing hypothesis that an unidentified energy system, potentially artificial in origin or naturally occurring in an unconventional way, could be operating beneath Greenland's ice sheet. The idea isn't necessarily of science fiction's glowing alien reactors humming beneath the tundra, but rather of anomalous energy exchanges produced by as yet unknown physical processes. Some theorists have speculated about ancient natural reactors, geological formations that, under the right conditions, can sustain low-level nuclear fission without human intervention. While rare, these phenomena have precedent. The Oklo Natural Nuclear Reactor in Gabon, Africa, discovered in the 1970s, proved that nature, given time and the perfect recipe, can indeed run its own atomic furnace. If similar conditions were ever present beneath Greenland, high concentrations of uranium, the presence of a moderator like groundwater, and precise geological containment, then it's possible that a natural reactor could have formed eons ago and is only now reawakening due to shifts in pressure, water infiltration, or seismic agitation. This could theoretically explain the heat signals, the odd electromagnetic readings, and even the variability in how those signals are received. What makes this idea even more fascinating is Greenland's geological obscurity. Much of its bedrock is still poorly understood compared to other parts of the world, hidden beneath layers of ice that have rendered direct study almost impossible. Satellite imaging and ice-penetrating radar offer hints, strange anomalies in density, heat flux, and mineral content, but none of them provide definitive answers. It's a blank canvas that invites speculation, and in that speculative space, the idea of forgotten natural forces or ancient georeactive phenomena begins to gain a whisper of credibility. There's also the matter of sub-ice structures that remain poorly mapped. Over the last decade, several unexplained geometric formations have been identified beneath Greenland's southern basin, structures that appear too linear and too sharply contoured to be attributed purely to glacial carving or sedimentary layering. While mainstream consensus leans toward unusual but natural geological formations, a small contingent of researchers believes these shapes might be the result of past technological processes, perhaps long since buried or abandoned by ancient civilizations we have no records of, or, more speculatively still, by non-human intelligences that once interacted with Earth. Though wildly speculative, the theory doesn't demand full belief in extraterrestrial contact or lost hyper-advanced societies. It could instead point toward undiscovered ancient human activity, long before our recorded history, when early civilizations may have achieved fleeting technological peaks that we've yet to fully recognize. The residual heat patterns, in this view, would be not the result of contemporary geology but the dying embers of ancient energy systems, long extinguished but still radiating their last ghostly warmth through the ice and rock. This notion is reinforced by the localized nature of some heat anomalies. In a recent study, researchers observed that specific pockets of thermal elevation didn't follow the expected gradients that geothermal systems usually produce. Instead, they emerged in isolation, like silent beacons beneath the ice, too hot to ignore, too isolated to explain. If there was once a source of intense energy beneath the Greenlandic crust, could we be witnessing the final echoes of its operation? Could the ice sheet be concealing a technological fossil, preserved under pressure and time? Even skeptics concede that Greenland is an ideal vault, its perpetual ice acting as a shield that could preserve underground secrets for tens of thousands of years. Whether natural or artificial, any structure or anomaly beneath the ice would remain hidden from erosion, untouched by surface weathering, and virtually inaccessible to humanity until very recently. This isolation raises the possibility that unknown processes have been unfolding beneath Greenland, uninterrupted for millennia, only now brushing the edges of detectability thanks to advancements in sensing technology. Furthermore, the geochemical composition of Greenland's subsurface has yet to be exhaustively catalogued. Some geologists have hinted at elevated readings of rare earth elements and other anomalous isotopes in nearby sediment samples. While these might simply be odd quirks of local mineralogy, others argue they could indicate residue from exotic energy interactions, be they nuclear, magnetic, or something else entirely. These residues don't line up with known volcanic emissions or hydrothermal vents, prompting some researchers to ask if we might be looking at a heat source that doesn't belong to the standard geothermal playbook. In essence, we find ourselves in a peculiar intersection, where geology meets speculation, and where science cautiously reaches out toward the mysteries that instruments cannot yet fully explain. The truth may be mundane, a rare alignment of mineral deposits and ancient tectonics, or it may be something far stranger, concealed beneath thousands of meters of glacial silence. And until we can drill deeper, scan more precisely, and build better models, the true source of Greenland's anomalous underground heat will remain a mystery, one that sits on the very edge of scientific understanding and speculative possibility. If these underground heat anomalies prove to be more than just a quirk of geology, if they truly signify something deeper, more complex, or even unknown, then the implications for humanity could be far-reaching and profound. It is rare that discoveries with such hidden depth make themselves known, especially in one of the most inhospitable and remote regions of the world. And yet, it is often in those untouched corners of the earth where the most paradigm-shifting insights can be found. To begin with, the potential climatic consequences of such underground activity are far from insignificant. Greenland's vast ice sheet plays a critical role in Earth's global climate regulation system. It acts not only as a reflective mirror that bounces sunlight back into space but also as one of the largest reserves of fresh water on the planet. If internal heating beneath this icy mass increases, regardless of the origin, then melting could accelerate in ways we are not currently prepared to face. While climate change is already warming the Arctic from above, what happens when the warming also comes from below? A two-front assault, both from atmospheric heating and internal geothermal flux, could destabilize Greenland's ice mass much faster than previously modeled. That, in turn, would feed directly into sea level rise. And not gradually, but potentially in punctuated bursts. As subglacial lakes drain, ice fractures deepen, and massive sheets cave away into the ocean with growing frequency. For low-lying coastal cities and island nations, the stakes could not be higher. But climate is only one piece of the puzzle. On a geopolitical level, the situation becomes equally intriguing. If Greenland's underground activity is tied to rare minerals, geothermal energy, or even undiscovered forms of energy, natural or artificial, then interest in this icy landmass is bound to intensify. Already, major world powers have taken a keen interest in the Arctic region, not just for its dwindling sea ice and shipping routes, but also for its untapped resource wealth. The detection of heat signals, especially those that hint at deep, isolated energy sources, could spur a new wave of scientific expeditions, military outposts, and international treaties or disputes over ownership and exploration rights. Nations that control or influence Greenland's interior could find themselves with access to resources, or secrets, that others cannot reach. If this energy turns out to be usable, or at the very least uniquely observable, it could inspire a new scientific frontier, akin to the race for Antarctica in the 20th century or the Moon in the space age. Suddenly, Greenland might not be just an icy expanse of interest to climatologists and glaciologists, but a key node in the future energy and technology landscape. Even more provocatively, if these heat anomalies are somehow linked to ancient energy systems or relics of past civilizations, natural or otherwise, the implications for our understanding of human history would be staggering. Mainstream archaeology largely operates under the belief that human civilization, as we know it, is only around 6,000 to 10,000 years old. But the discovery of something artificial, mechanical, or structurally organized beneath Greenland's deep ice would force a rethinking of our entire historical narrative. Could it be that humanity's origins are deeper, more technologically advanced, and more complex than we currently imagine? Could our species have experienced past rises and falls, lost cycles of civilization buried beneath sediment, ice, and time? This is no longer just the stuff of myth or fringe theory. Increasingly, archaeological anomalies around the world are challenging the linear progression model we've accepted for decades. If Greenland holds even one artifact, one signal, or one inexplicable structure, it could ignite a wave of global scientific reevaluation, sending historians, linguists, engineers, and physicists scrambling to rewrite textbooks and theories long thought settled. But even absent direct evidence of ancient civilizations, the discovery of unknown energy sources or physical phenomena operating in uncharted ways could revolutionize our understanding of planetary science. It could point to the possibility that Earth still holds vast secrets, not just in the depths of its oceans or the recesses of its mantle, but beneath sheets of ice we've barely scratched. If heat signals can originate without obvious volcanic activity, without tectonic friction, then we may need to consider that our geophysical models are incomplete. What other anomalies lie beneath Antarctica? Under the Himalayas? Beneath the deserts? This realization could spark a renaissance in exploration, much like the space race did decades ago. But instead of aiming upward, we'd be digging down, developing new drilling technologies, deep ice radar, subglacial drones, and AI-based interpretive systems to peel back the layers of our own planet's surface. In doing so, we could encounter entirely new realms of microbial life, unknown forms of mineralization, and perhaps even mechanisms of heat and energy transfer that operate independently of the systems we've cataloged. And yet, there is also a psychological and cultural impact to consider. Human beings are shaped by our understanding of the world. When that understanding is challenged, whether through the discovery of alien worlds, the depths of quantum mechanics, or anomalies beneath the polar ice, it forces us to confront our limitations. It pushes us to evolve intellectually, philosophically, and spiritually. The mere suggestion that Greenland's underground heat may come from something unexplainable causes a ripple across all disciplines. For scientists, it's a challenge to seek truth in complexity. For the public, it becomes a mystery to be solved, a narrative that captures imagination. And for philosophers and theologians, it opens the door to questions about the origin of life, intelligence, and the uniqueness of our civilization in the timeline of the universe. Whatever the cause of these heat signals, be it tectonic, nuclear, artificial, or something more exotic, it reminds us of our humility in the face of nature's vastness. It reminds us that even now, in the age of satellites and particle accelerators, we are still discovering the Earth, still learning, still seeking. And in that pursuit, Greenland may very well be the next great chapter. Now that we've explored the implications of the anomalous underground heat signals beneath Greenland, it's time to turn our attention to what could potentially be done to address this phenomenon, whether through scientific investigation, technological advancements, or more proactive environmental and geopolitical strategies. The sheer scale of the mystery, combined with its potential consequences, calls for a multifaceted approach to understanding, mitigating, and adapting to whatever is happening beneath the icy surface of Greenland. The first and most immediate step in combating or even understanding the anomaly is a comprehensive scientific investigation. This could involve expanding the current research efforts in Greenland to specifically focus on detecting and analyzing these heat signals, their source, and their potential impact. Given the complexity and the remoteness of Greenland's interior, gathering more data would be challenging, but it's not impossible. One of the most immediate tools that could be employed is geophysical monitoring. Teams of scientists could deploy an extensive network of sensors designed to detect seismic activity, heat emissions, and any electromagnetic disturbances that might be associated with the anomaly. These instruments could be placed across the Greenland ice sheet, especially around known hotspots, to better track fluctuations and pinpoint the exact locations of these anomalous heat signatures. This would require significant investment, but the technology to do so exists, though more advanced versions may need to be developed. For instance, deep penetrating radar, ground penetrating radar, GPR, and satellite-based thermal imaging technologies could offer insights into the underground heat distribution and how it correlates with changes in the ice sheet structure. In addition, remote sensing technology would play a critical role. Satellite imagery could provide real-time updates on how the heat sources are affecting the surrounding environment. By monitoring temperature variations over time, scientists would be able to track how heat spreads, whether it has a direct correlation to glacial melt, and what potential effects it has on the surrounding terrain. It may also help identify any patterns of geothermal activity, such as volcanoes or hydrothermal vents, that were previously unknown. The aim of this scientific approach would not only be to understand the nature of the anomaly itself but also to assess the potential risks it poses to the environment, climate, and human activity. For example, if these heat signals are linked to rapidly accelerating ice melt, the next logical step would be to begin modeling the impacts of that on global sea levels, local weather patterns, and the stability of Greenland's ice sheet. This would give scientists valuable insights into how much time we might have to adapt to potential changes and, just as importantly, what mitigation strategies can be put in place to limit the damage. If the heat anomaly beneath Greenland turns out to have serious implications, whether from a melting ice sheet or the unearthing of previously dormant energy sources, there are a number of technological solutions that could be explored to mitigate, or at least control its effects. One of the more immediate concerns would be the potential destabilization of the Greenland ice sheet. If underground heat is accelerating the melting process, it could threaten the structural integrity of the ice, leading to the calving of massive icebergs and contributing to rising sea levels. To counteract this, a variety of geoengineering techniques could be employed. These might include ice sheet reinforcement, which would involve using advanced technologies to prevent or slow the melting process. For example, researchers have proposed injecting water beneath the ice to create a layer of artificial support, preventing further ice loss. Alternatively, large-scale deployment of cooling systems or reflective surfaces might be used to maintain the stability of the ice. While these ideas are still in the conceptual stage, international cooperation and funding could allow for the development of scalable, cost-effective methods to address the issue. before the full force of accelerated melting takes its toll. On a more speculative front, if the heat signals detected beneath Greenland are linked to geothermal sources or geothermal energy systems, this presents an opportunity to harness that heat as a renewable energy source. Rather than seeing this anomaly as a threat, we could explore methods of capturing and utilizing geothermal energy for local communities in Greenland or, in the long term, on a larger scale. Advances in geothermal drilling technology could help tap into the heat source and convert it into usable electricity. This would not only provide a clean, sustainable energy source for the region but also help to mitigate the growing reliance on fossil fuels for energy production. Though this approach would require substantial investment in infrastructure, it holds the promise of addressing both energy and climate concerns in one stroke. Tapping into underground heat could reduce carbon emissions by shifting energy production away from fossil fuels, and in the case of Greenland, it could offset the need to transport energy over vast distances, bringing energy independence to a region that has been heavily dependent on outside resources. In the worst-case scenario, where the anomaly leads to extreme and irreversible changes if the anomaly triggers an influx of fresh water into the ocean from the ice melt, it could disrupt ocean currents and significantly affect marine ecosystems. Here, monitoring the effects on global marine biodiversity would become crucial, and measures could be taken to protect species that might be at risk. Additionally, global food security could become an issue as changing ecosystems alter fishing grounds, so international cooperation would be needed to ensure that the consequences of this anomaly don't lead to economic instability. Finally, a critical component in addressing the anomaly and its potential impacts would be international cooperation. Greenland's position as part of Denmark, combined with its importance to global climate and ocean systems, makes it a key player in the broader environmental puzzle. As the heat signals potentially indicate a growing, interconnected global crisis, it would be important for nations, especially those with an interest in the Arctic region, to come together to share information and coordinate responses. A multilateral approach, supported by scientific collaborations, could help ensure that this anomaly doesn't lead to conflicts over resources or geopolitical instability. Research funding, data sharing agreements, and joint efforts to explore and mitigate the risks of the anomaly could foster a spirit of collaboration that might serve as a model for other climate-related challenges in the future. As we reflect on the anomalous underground heat signals detected beneath Greenland, it's clear that the mystery surrounding this phenomenon offers more than just a scientific puzzle. It holds profound implications for humanity's future. At the heart of this anomaly is the complex intersection of our planet's natural processes, the unknown forces that shape our environment, and the ways in which these forces are intricately woven into the fabric of our existence. The detection of these unusual heat signals in Greenland has set the stage for a deeper understanding of the forces beneath the Earth's surface and the changes occurring in some of the planet's most remote regions. The theories we've explored, from geothermal activity to the possibility of ancient heat sources, and even speculative ideas of something more extraordinary, remind us of the vastness of the unknown. Each theory, while different, paints a picture of a world that is full of hidden complexities, many of which we are only just beginning to understand. We've delved into the idea that the heat could be related to geothermal activity, as heat from beneath the Earth's crust rises, potentially influencing the stability of Greenland's massive ice sheet. The more we look into this, the more we realize the delicate balance that governs our planet's systems. From global sea level rise to shifting climate patterns, the impact of this anomaly could be far-reaching, requiring unprecedented responses from both scientists and governments. If the heat beneath Greenland is, in fact, the trigger for destabilizing ice and accelerating melt, the world faces a future that will demand significant adaptation to protect vulnerable populations, coastal cities, and ecosystems that rely on the natural equilibrium we've long taken for granted. At the same time, we've also considered the possibility that this anomaly is part of a broader, more speculative scenario, perhaps even something far beyond the normal bounds of scientific understanding. Whether it's the unearthing of ancient forces or a novel geological process at work, these ideas push us to explore the boundaries of what we know about Earth's inner workings and what might exist beneath the surface. They call attention to the fact that our planet is a vast, evolving entity, one that has secrets yet to be uncovered. What these theories and possibilities remind us is that our relationship with the Earth is not static, it is ever-changing. Our understanding of the world around us is constantly evolving, and with it, so too must our ability to respond to the challenges that arise. Whether it's through scientific innovation, technological advancements, or collaborative global efforts, the future of humanity's interaction with Earth lies in our hands. As we move forward, the anomaly beneath Greenland also presents an opportunity for scientific growth and innovation. As we harness the power of technology to monitor, analyze, and adapt to the shifts in our planet's behavior, we are given a chance to redefine our approach to both climate change and geothermal energy. In seeking to understand these heat signals and their potential impact, we could unlock the means to better protect our planet while simultaneously tapping into sustainable energy sources that could alleviate global energy crises. The lessons learned here could ripple across many other aspects of our environment, from reducing carbon emissions to protecting biodiversity. Moreover, the global implications of this anomaly serve as a call to action for international cooperation. Just as the Earth's natural systems are interconnected, so too must our efforts to protect and preserve the environment be. We live in a world that is more interconnected than ever before, where the actions of one nation can impact the entire globe. The potential environmental consequences of Greenland's heat anomaly are not isolated to one region or country. They are a reminder that the challenges we face are global, and only by working together can we hope to address them. In the end, the question of what this anomaly means for humanity is not just about the scientific or technological responses we can make. It's also about how we choose to act collectively in the face of challenges that, though daunting, also present us with the opportunity to rise to the occasion. There is no single answer to the mystery beneath Greenland. However, there is a path forward that involves innovation, cooperation, and a deep commitment to understanding the world we share. Through all the complexities of this phenomenon, we are reminded that our relationship with the Earth requires respect, responsibility, and a willingness to adapt. The anomaly beneath Greenland, whether it is a natural occurrence, a shift in geothermal energy, or something even more speculative, beckons us to look beyond what we know and to continue exploring, learning, and evolving. It's a story that asks us to think beyond the present moment and consider the broader narrative of humanity's place on this planet, how we shape it, how we protect it, and how we choose to respond when faced with the unknown. Ultimately, the ongoing investigation into these mysterious heat signals is not just about finding answers. It's about preparing for a future that may be as unpredictable as it is inevitable. It is a reminder that, no matter how much we understand or don't understand about the Earth, we must approach our world with humility, curiosity, and a commitment to ensuring that future generations are equipped with the knowledge and tools to live in harmony with the forces that shape our planet. If you've made it this far, thank you for diving deep into this fascinating mystery with us. The world beneath the surface of our planet holds so many secrets, and as we continue to explore, we're reminded that there's so much more to discover. If you found this exploration intriguing, don't forget to like and subscribe for more content on the most mysterious phenomena and the cutting-edge science that seeks to unravel them. By subscribing, you'll stay up to date with our latest videos, theories, and discoveries, so you never miss out on the thrilling stories that could shape our understanding of the world and the future we share. Thanks for watching, and as always, stay curious, stay informed, and keep exploring with us.